Welcome to this session on mathematical logic. In the previous session, we discussed about the arguments and how to prove the validity of the argument using the truth table. Just to have a quick recap, an argument is a sequence of propositions called the premises, denoted usually by P, P1, P2, P3 up to let us say Pn. These are the premises these are the propositions which are called the premises, and it is followed by the symbol, and the proposition following this symbol is called the conclusion. So this is an argument, and the argument is considered to be valid if P1 conjunction P2 conjunction P3 conjunction Pn implies C is a tautology. So we have seen in the previous session that one of the ways to verify the validity of the argument is by making the truth table of all the premises and the conclusion. And in the truth table, all the rows where all the premises, the rows of the truth table where all the premises are true are called the critical rows. And if the conclusion is true in all the critical rows, then the argument is said to be a valid argument. And if the conclusion is false even in a single critical row, then the argument is said to be an invalid argument. We also saw that this method has a disadvantage, that it fails if the number of propositions becomes large, because for a argument containing n number of propositions, the n number of premises, the truth table is going to have 2 to the power n rows in the truth table. So this method can be used as long as the number n is small. Let us say we have 4 propositions, then we will have 16 rows in the truth table. If we have 5 propositions, then we are going to have 32 rows in the truth table. And as n becomes more, making a truth table to check the validity of the argument becomes more and more impractical. We have to use the second method of checking the validity of argument, that is by using the laws of inference. Let's start. So again, a quick recap. An argument is an assertion that a given set of propositions P1, P2 up to Pn yields another proposition Q. Right? These are called the premises and Q is called the conclusion. This is the symbol that separates the premises from the conclusion. It may also be written like this. Right? These are the premises and followed by this symbol, which you might remember is the therefore symbol, followed by the conclusion. So one way for checking, let's repeat, one way for checking the validity of the arguments is by making a truth table. Now, in case the number of propositions becomes more and the truth table method cannot be used, we are bound to use some other method, and that some other method is provided to us. So these are the inference rules. The first inference rule is called the modus ponens. Now, they have got some quite strange names, most of the rules of inference. This is called the modus ponens. Now, modus ponens says there are two premises over here. The first premise is the proposition P, and the second premise is the proposition P implies Q. If this is true and this is true, therefore Q. We already know in case of a implication, in case of an implication, if I'm writing an implication like P implies Q and I know that this is true, then the implication is going to be true if and only if this is also true. So if I say this is true and the implication is true, that means Q is bound to be true. So this is a pre-proven result. So this is the modus ponens. The modus ponens says if the proposition P is true and the proposition P implies Q is true, then we can conclude Q. We'll see them in a little bit more detail. Just let us list all the rules of inference. The second rule of inference is called the modus tollens, which says if Q is false, it means negation of Q is true, that means Q is false, and P implies Q is true, then P is also false. This actually comes from the contrapositive. We know that the implication can be written as the contrapositive, which is not of Q implies not of P. Now we say that these two are logically equivalent. Remember in the previous lecture we showed that these two are equivalent to each other. So if we say that P implies Q is true, that is given over here, and not of Q is true, then by the law of implication, this is bound to be true. So not of P. Modus tollens. Next we have hypothetical syllogism, which says if P implies Q and Q implies R, then by transitivity, here we call it hypothetical syllogism, we say that P implies R. Then we have disjunctive syllogism, which says if P or Q is true, if P or Q is true and P is false, if P is false but P or Q is true, that automatically means that Q must be true. If Q is also false, then this entire proposition will become false and the premise will be violated. So if this premise is true and this premise is true, then the conclusion is that we have Q is true. Then the next, these four rules, they have quite simple names. One is the addition. It simply says if the proposition P is true, if the proposition P is true, then the preposition where P is being odd by any other preposition is also true. Obviously, if P is true and it is the property of the OR operation or the disjunction operation, if one of the inputs is true, then whatever be the other input, the output is always going to be true. So if P is true, if I OR it or if I apply disjunction to P along with any other preposition, the result is always going to be true. Next, we have the simplification operation. It says if P and Q is true, remember AND operation, this is going to be true if and only if this is true and this is true. So this is the conclusion. I could have also written it something like P and Q. I could also write it like therefore Q. Right? It does not make any difference. Then we have conjunction. If P is true, Q is true, then P and Q is true. Simple. We have resolution, which says if P or Q is true and not of P or R is also true, then we can conclude Q or R. I'll repeat, if P or Q is true and not of P of and R, sorry, not of P or R is true, then Q or R is true. Right? Now let us see these rules of inference in a little bit more detail before we can actually go into how to apply these rules. Let's go into these rules with a little bit more detail. The inference rules are truth preserving. Truth preserving means if the left hand side is true, then the right hand side is also true. Let me show it to you. Say we write modus ponens, like the modus ponens says P, comma, P implies Q, the conclusion is Q. This is the left hand side and this is the right hand side. We say if left hand side is true, then the right hand side is also true. So when we say if left hand side is true, that means if this is true and this is true. Remember, the argument actually means P and P implies Q. This is the premise implies Q, right? If this is true, then this is bound to be. It is applied always to the true statements. Modus ponens, right? Modus ponens, the first premise is P, the second premise is P implies Q, and the conclusion is Q, right? These are the premises. This is the conclusion. Let's take a simple example. Let us say P is showing it is sunny, Q is showing it is hot. And P implies Q says it is hot whenever it is sunny, right? So now, if it is sunny, it must be hot, right? So we say if P implies Q is true, if P implies Q is true and P is true, Q, it is hot whenever it is sunny. Or I can write it as if it is sunny, then it is hot. If this is true and it is sunny is true, then the conclusion is it is hot. Another important point. It is not necessary that these premises be simple atomic propositions. They can be compound propositions also, as is shown in this example. Now A or negation of B implies negation of C. Let us say this is the premise. A or negation of B, this is yet another premise. Let us say this is the premise and this is the premise. Now if you see this A or negation B, right? If I consider this to be the premise capital P, if I call it capital, let us say capital P, and negation C, if I call it, let us say capital Q. So this actually means capital P and P implies Q. So I can apply modus ponens on both of them and the conclusion would be Q, that is negation of C. So understand, it is not necessary that the premises be atomic propositions. They can be compound propositions also. Let's see one more example. If I give you a premise like P and we say P and Q implies R. Now I cannot apply modus ponens here. Why? Because this P and Q, P conjunction Q, in the previous slide, remember we said that they have to be literally applicable. Right? So if we have a P over here and we have P and Q over here, right? So we cannot apply modus ponens over here. If we have P over here, not P and Q, then I could have applied modus ponens, but not in this case. Let's see the other one, modus tollens, which says if not Q and P implies Q, then not P. It says not Q, P implies Q, and the conclusion is not of P, right? Once again, P is it is sunny, Q it is hot, and P implies Q says it is hot whenever it is sunny. If it is not hot, right? If I assume this to be true and I say it is not hot, then I can conclude it is not sunny. Please remember the contrapositive for an implication is same as the implication. If I just simply write P implies Q, if this is the implication, then Q implies P was the converse. Not of P implies not of Q was the inverse. And not of Q implies not of P was the contrapositive. And this are equivalent. This and this are equivalent. Right? So once again, this is how you write modus tollens, negation of Q, P implies Q. These are the two premises and the conclusion will be negation of P. Once again, it is not necessary that the premises be atomic propositions. They can also be compound propositions. Like if I say C implies A implies B and then I say negation of A implies B, right? So this is the if part, this is the then part, and then I have the negation of the then part, then I can have the negation of the if part. Hypothetical syllogism, which says if P implies Q and Q implies R, we can conclude that P implies R. So if P says it is sunny, Q says it is hot, R says it is dry, and we say P implies Q, it is hot when it is sunny, QR, it is dry when it is hot, then I can say it must be dry when it is sunny. If sunny implies hot and hot implies dry, then sunny implies dry. Right? Once again, the propositions need not be atomic propositions. You can have compound propositions. Disjunctive syllogism, if P or Q and not P, then Q. If P or Q says it is hot or sunny, and then we say if it is not sunny, right, then it is hot. If I say P or Q, that means it is hot or it is sunny, and the second premise says not of not sunny, not of P, then the conclusion is if this is true, if this is true, that means, see, this is a disjunction. If this is true, that means this is true or this is true or both of them are true. If both of them become false, this entire compound proposition becomes false. And now if I say P is false, then Q is bound to be true, because if Q also becomes false, then this entire premise becomes false, right? And which goes against our assumption. We assume that the premises are true. Once again, the premises need not be atomic propositions, they can be compound propositions also. Next, we have the resolution. If P or Q and not P or R, then Q or R. If we say sunny, Q says it is hot, R says it is dry, then we say P or Q, it is sunny or hot, Q or R says it is not hot or it is dry. Given the above, the propositions say if it is sunny or hot but not sunny or dry, it must be hot or dry, right? If you see over here, resolution says P or Q, resolution says P or Q and not of P or R. P or Q, not of P or R, right? So let me write it once again over here. If it says P or Q and not of P or R, then the conclusion is Q or R. So if we say if it is sunny or hot, if it is sunny or hot but not sunny or dry, then it must be hot or dry, right? This is a little bit tricky law of inference. It is not as obvious as the other ones. You just have to need to practice it, remember it, and we will see how to apply these. Addition, quite a simple one. If P, then P or Q, right? It simply says it is sunny, Q says it is hot. If it is sunny, then it must be hot or sunny. Simply, this is obvious. If P is true, if P is true, then if I apply disjunction on P with anything, if this is true, then the disjunction is bound to be right, because disjunction means if one of the inputs is true, then the entire thing is always simplification. If P and Q is true, if this is true, this is the conjunction operation and operation. It means this must be true and this must be true. This is the property of the AND operation, that both of them have to be true for this entire proposition to be true. So this is also true and this is also true. So if this is the premise, then the conclusion can be either P or the conclusion can be Q. It is sunny, it is hot. If I say it is hot and sunny, then it must be hot. I can also say it must be sunny. Finally, we have the conjunction. If P and Q, then P and Q. If P is true, Q is true, therefore P and Q is true. If it is sunny and it is hot, it must be hot and sunny. That is obvious. If this is true, then the conjunction operation is true. So these are the various laws of inference, right? Let's have a small test. These are certain statements. Now we will see which rule of inference is being used in each argument below. Now the simple way of performing this is, once you are given a question like this, you have to identify the propositions. Alice is a math major, therefore Alice is either a math major or a CSI major, right? So Alice is a math major, let us call it P. Alice is a math major, once again P, or a CSI major, let us say Q. So it says P, this is true, then P or Q, right? Sorry, this is the conclusion. Therefore, this word indicates whatever is following is the conclusion. Can you identify the rule over here? Can you identify? Yes, this is the addition. Jerry is a math major and a CSI major. Therefore, Jerry is a math major, right? So I say P and Q. Therefore, P. Jerry is a math major, we are calling it P. Jerry being a CSI major, we are calling it Q. So this statement says P and Q. Jerry is a math major and a CSI major, P and Q. Therefore, this is where the conclusion starts. Jerry is a math major. Can you identify the rule? Can you? Of course, it is the simplification. If it is raining, P, then the pool will be closed, Q. It is rainy. This simply says if it is rainy, then the pool will be closed. P implies Q. It is rainy. Once again, comma, P. Therefore, the pool is closed. Right? Quite simple. P implies Q and P, therefore, Q. Remember, what is this? Can you identify? This is the modus ponens. If it snows today, P, the university will close, Q. P implies Q. The university is not closed, not of Q. Therefore, it did not snow today, not of P. So it is saying P implies Q, comma, not of Q, therefore not of P. Can you identify the rule over here? Right, that is modus tollens. If I go to swimming, P, then I will stay in the sun too long, Q. So this says P implies Q. If I stay in the sun too long, that is obviously Q, then I will sunburn. It says Q implies R. Therefore, if I go swimming, P, then I will sunburn, R. Yes, you are right. This is hypothetical syllogism. Then, if I go swimming, P, or I eat an ice cream, Q. P or Q. I did not go swimming. I did not go swimming. That means not of P. Therefore, I eat an ice cream, Q. Yes, just it right. This is the disjunctive syllogism. So, you have correctly identified the different rules from the statements. Now let us see one example of how these will be applied to check the validity of an argument. Then, we have been given certain premises: x, x implies y implies z, not of z or w, and we have to prove the conclusion w. We have to show that these premises, premise 1, premise 2, premise 3, premise 4, these premises, from these premises, I can infer the conclusion W. Right? Let us see how we'll do it. Right? This X implies Y. This is the premise P2. Y implies Z. This is the premise P3. Now, X implies Y and Y implies Z. So, I can apply hypothetical syllogism to come to X implies Z. Right? So, we call it, let us say, we are applying hypothetical syllogism on 1 and 2. Then X, once again, is the premise P1. If X implies Z and X, X implies Z and X. So I can apply modus ponens on these two to come with Z. So another law has been applied over here. Now Z is true and not of Z or W is true. Z is true and not of Z or W is true. Right? Please remember, what does disjunctive syllogism look like? Disjunctive syllogism looks like P or Q and not of P, therefore Q. Okay. Now see, this says Z. This says Z and this says not of Z or W. Not of Z or W. Right? And Z. This P, where we had P over here, here I am having not of Z, and where I had not of P, I am having Z, which is actually not of Z. So disjunctive syllogism is applicable over here. So what I'll concur? I'll confer the W. So This is the final conclusion, and this is what we started off to prove. So by applying these three rules, hypothetical syllogism, modus ponens, and disjunctive syllogism, we have proven the conclusion. Now I'm not giving you more examples over here. I just want you to go through this entire video once again, familiarize yourself with the different rules of inferences. And what are the different rules of inferences? If I just have to list them: conjunction, simplification, addition, resolution, disjunctive syllogism, hypothetical syllogism, modus tollens, and modus ponens. I suggest you make a list like this. You make a list like rules of inference, you make it on a piece of paper, so that whenever I am solving a question, I have that list as a ready reckoner with me. In the next video, in the next lecture, we are going to solve some more examples by using these rules of inference. Till then, thank you.